Uh, Today, welcome back to the third session of deep learning. The topic of today's lectures are the following. First, I'm going to talk about convolutional neural networks. Then I will talk about recurrent neural networks. These are some of the very popular types of neural networks for particular applications. Then I will talk about word vectors or word embeddings. And then in the second part of the lecture, I will talk about ongoing work at the Google Brain project. Okay. Okay. So before I begin, I want to revisit some of the topics that we discussed yesterday. The first topic was, some practical advice of how to train neural networks. Then I, discussed of the usefulness of having neural networks, namely, you can classify nonlinear data. Okay. And then I talk about deep learning, some definitions of deep learning. Why is it related to neural networks? Then towards the end, I talk about the idea of autoencoder, an unsupervised learning algorithm. And then I'll talk about the idea of pre-training. So maybe there was a bit of confusion towards the end about autoencoder, pre-training, and so on. So maybe I talk about that and then start today's lecture. So yesterday, I was talking about the idea of autoencoder. So autoencoder, so you have some input, maybe a vector of 3 or 4 dimensions, this, and then you have a neural network. So you're trying to learn the matrix W, W1, W1, maybe W, maybe another W. Let's call it a different matrix, W and V. You want to learn W and V in such a way that X prime is very close to X. So you minimize, during training, your goal is to minimize the distance between X and X prime, right? And X prime is a function of X and W and V, right? Okay, that's autoencoder. So this is a shallow autoencoder with one hidden layer, right? Trying to learn the encoding that can reconstruct the input. Now, around 2006, people use it for something called pre-training. So the idea of pre-training is as follows. So let's suppose that you have a deep network. Right. Let's suppose that you have a deep network like that, right? And you have W1, W2, W3 that you would like to train, right? Maybe at the end you want to predict some label, okay? It turns out with a deep network like that, if you have random initialization, it might take a long time to train, or maybe it will converge to bad local minimum, okay? So people say, well, an idea to use unlabeled data to come up with better initialization for W1, W2, W3 is as follows. So first, you take this network out, and then you train autoencoder that looks like that. Okay. So W1 prime is another matrix, right? You learn, but then after you're done training, you remove it from the training. And after you're done training, you end up having W1. Then you multiply with your data, right? And then you do feed forward, and you end up with H1 of X, okay? And then you use H1 of X and then you take this matrix out, right? And then And then you learn right, and this is h1 of x. Okay, this is another autoencoder. Okay, and then you learn W2. So after having W2 and then W1, then you do a feed forward one more step to have the this layer, and then you keep going. Is this unclear? Yeah, I have a question.
If you found a good, for example, your diagram here, a good three-dimensional representation of four-dimensional input,
Yeah.
why go back to a four-dimensional space? Why not just work in another dimensional space from that point onward?
Oh, so you saying why don't you?
So once you've learned that representation, you already have a good three-dimensional representation.
Here, which one? Yeah.
So why not just work with that in your supervised algorithm instead of?
Oh, I see. So why don't you tag on the label just right here, right? Sure. Is that the white label? Well, the idea of having a deep network versus a shallow network is that what I told yesterday. If you want to have a good shallow network, right, you need a lot of neurons in one layer to model that. Whereas if you have a deep network, you might need less neurons per layer. Right? So if you stop here and then trying to learn why, maybe why is so nonlinear that you need a lot of these neurons. Right? But if y is nonlinear, then another way to do it is to have a deep network. And you could learn end to end, but it's too difficult. So you have to make it layer-wise pre-training to approximate. To trying to reconstruct X, and then after that, trying to actually learn Y. Is everything? Yeah, question? Mm-hmm. Here? Mm-hmm. That's a very good question. So the first answer is because it's nonlinear right here, it might not be exactly identity, but I have another answer for that. Okay. So it turns out that so far, what I've just told you is, input, and then maybe in the next layer, the number of neurons can be smaller than the previous layer. It's kind of getting smaller like that, right? But sometimes you don't have that. Sometimes you want something like this. This is input, right? And then sometimes you want something like that, right? Or maybe more. An autoencoder with a hidden representation larger than the input is very redundant, right? So it's very redundant. What it learned is basically trying to, make W1 an identity function and the rest being zeros or something like that, right? So it's not useful to actually learn W1 when this is very redundant like that. So a way to avoid that is using something called sparse autoencoder. The idea is so there's many variations of sparse autoencoder. One is basically just say, in addition to the reconstruction objective, right? It's in addition to the reconstruction objective where you have X and then W1, right? You really want the hidden let's denote this H of X, okay? You want H of X to be sparse, right? Namely, you could have an L1 penalty on your H of X. Okay. It's like penalizing the absolute value of h of x. Okay? And then what you end up is a redundant representation maybe, but very sparse. Right? For a given input, maybe a few of the pixel, a few of the neurons will be non-zero, but the rest will be zero. Okay. So L1 is one kind of penalty on the hidden representation, but many people use other kind of penalty, for example, L0, or maybe the KL divergence between H and some target distribution. So if you Google for sparse autoencoder, you end up with all the variations, but maybe I just want to talk about one variation in this lecture. Is that okay? Okay. Any other questions? Yes. Can you ask the question again? I didn't hear that very well.
When you say that the next hidden layer, when you add more nodes to it,
Uh-huh.
then it becomes redundant, does that mean that the form is overcomplete?
Yeah, it's overcomplete. So this is overcomplete, right? So the number of output is much larger than the number of input, so it's totally redundant if you don't enforce any sparsity. Okay.
I mean, that wouldn't be the case if you have multiple hidden layers.
Pardon?
That wouldn't be the case if you have multiple hidden layers. One hidden layer is passing down more.
Yeah. You only do this if you have one of the layer being overcomplete. Yeah. Any other questions? Okay, great. So let's talk about convolutional neural networks. Some people also use the term ConvNet. Right? So if you Google use literature, sometimes you see the word ConvNet somewhere. Right? So before around 2011, in computer vision, a lot of people use something called handcrafted features. So handcrafted features are something like shift, unhawk, and etc. And they work really well for small data sets. But it turns out that around 2011, after we use convolutional net and use good GPUs, the results of ConvNet are usually better than handcrafted features. And that gives like dramatic change in the field of computer vision. And I think and it is a very important concept to learn. So let's go back to our original idea of neural net, right? So let's suppose this is the input, right? So this is input. Could be an image, right? Maybe a 1D image for now, okay? And then you want to learn some representation, and then go on trying to predict the label, okay? So that's some representation, trying to predict the label. So and then every neuron will be connected to the input image, okay? A problem with this representation of this setup is that let's suppose that your input image is really big, right? Let's suppose that your input image is 100 by 100 pixels. Then this image is a 10,000 dimensional vector. Right? And then every neuron in here will have to get 10,000 connections. So let's suppose that you have like 1,000 neurons. 1,000 features is very small, right? Then you end up with 1,000 times 10,000, which is a lot of connections, right? This is 10 million connection. Right. So that is a very expensive representation. So people have thought about how to avoid that problem. And then look at images and they realize that pixels in a local region of an image are correlated with each other, but pixels are very far away are not correlated with each other. So let's give an example. Let's say I take a picture right here. Then the information around here will be very correlated, but the pixel here and the pixel over there are unlikely to be correlated. So they propose the first idea they propose is the idea of local receptive field. So again, let's suppose for now we have a 1D image, right? And then we have a neuron. Instead of connecting to everything in the image, right? Just only connect to only a few pixels, right? This is the top left corner of the image. This is the next area. There might be pixel here, something like that. Right? And then, with that idea, you end up with a representation that has less parameters compared to the original fully connected neural network. Right. So how do you do backprop with this? Right? Assuming that having local connection. So one way to do this, a very naive and simple implementation, is to suppose that all the connections are there, right? But they are zeros. And then you do matrix vector multiplication using sparse matrix vector multiplication, and then doing feed forward like normal. Right? And then when you do backprop, you will compute the gradient for all the parameters, but for the ones that are not connected, you don't update the parameters. Okay, so is it excuse me? Is it still seeable or is it too far away?
It's still okay. It's still good.
Up to right here?
Okay.
Yeah.
Oh.
Okay, here. Okay. Local. So here I say, assume that the network is just fully connected, but with zero weight for the empty connection. And then do forward prop. As usual. Right. You do forward like normal, and then back prop. As usual. And update. And then backprop as usual, but only update the parameters that are non-zeros. Right? Is that clear? Okay. So local receptive field network reduce the number of parameters significantly, but that's not too much. Now we can do even better. So what we can do, so let's suppose this is a network that I have, right? This is basically local, this is local network, okay? Another idea is to say that all these copies are the same. What I'm saying is that let's say this is W1, W2, W3, W4, W5, W6, W7, W8, W9. Then I will impose a constraint, say W1 equal to W4, W2 equal to W5, and W6, 3 equal to W6. And this is equal to W7. Right. So strictly speaking, these weights are the exact copy of these weights, and these weights are exactly square. And because this looks pretty much like a convolutional operation, right? You take this and then you replicate it in many space in the image, right? If suppose that you have an image that looks like that, then you have a weight that you keep copying in all the position of the image, and that action is called convolution. And that's really enhance the name convolutional net. Right. Now, how do you do backpropagation with convolution? Right. So I will tell you a naive implementation, but like a faster implementation, you can think about it later. Right. Right. So assume it is a local receptive field network. Right. So a ConvNet is basically a local receptive field network that I show you over there. Okay. And then what you do is you do forward prop. As usual. Okay, you do forward prop as usual. And then do back prop also as usual. Okay. And then after you're done, you have gradient of all these parameters. Okay. Then first you sum up the gradient. So you say dj over d, you do this action. You do dj over d1 plus dj over d4 plus dj over dw7. These are the weights that are shared with each other. Right? You sum it up, right? And that's the update for W1. Okay. And then you set W2, you set W4 in W1, and then you set W7 equal to W1, right? And then you do the same for all the things. Question?
Wouldn't it make more sense to average the gradient out?
It turns out that the sum is the correct gradient, but you could average too. That's basically changing the learning rate. Okay? Yes? Question?
Yes, so I'm trying to understand intuitively, you said that it's equal to 0, but you are actually considering them to be different, and that's why you are calculating the differentials against each.
Yeah. So yeah. When you do backprop, right, you get the gradient for this one,
Right.
you get the gradient for that one,
Right.
you get the gradient for that one, right? Because of backprop, right? But because they are shared, they are shared by this constraint, right? This is what I said it should be, right? And then you do something like that. Now, that's the naive implementation, right? Because I try to be really redundant, right? I say I have an explicit representation for W1, explicit representation, and so on. But you could be clever in your code not to have that, okay? But this is, mathematics, what it should look like first, right?
And the second question I had is, intuitively, why does this work? Why does representing just blue one instead of all those three? Why does that work? So I'm trying to understand that. There we assume the weights were 0.
Yeah.
And now here we are assuming. Right.
There's a couple of steps here. Number one is this connection is 0,
Yes.
right?
Yes, so that is the same as that one.
Right. So that's locality. Okay. So this is locality. This neuron doesn't look everything. Okay, that's cool.
That makes sense.
Okay. So the second question is why copying is a good idea. Okay. So that's a great question. So let's think about that. Why copying? So far I've just told you how to do math first, right? So let's think about why is it. So why is that a smart idea? So it turns out that in yes, pardon, SEL local receptive field, RL. Sorry, yeah. So first we wanna let's move one more step and say what do we do if the input is two-dimensional first. Okay. So far this is like a 1D image, but I want to do it for 2D. So for 2D, what you would see is something like this. So let's say you have an image, right? And again, the input is a bunch of pixels. Every pixel has some value, right? So it's a 2D input. Right? So a convnet on image is basically the same. So you have a neuron that look at 6 pixels here, and then you copy it over to the next position where so this neuron, the weight for it would be copied to another position. Maybe that doesn't seem clear. So maybe let's keep with 1D first. Then we could think about it. Okay. So it's hard to actually understand it in 1D, but I will try. Okay. So let's suppose that in 1D, if you have some pixel, if you have some object, but it moves. If it moves, so let's say you have an object right here, and the concept that this is the same object, but it moves downward for a couple of pixels. And you want your network to say, it doesn't matter where the object is in the image, but as long as it is in the image, just say 1, right? Then convnet is a good idea because this filter of that object is being copied over in different positions, right? But we need one more step. So that is just a convolution step. One thing that we could do is called max pooling. I need. So the convnet, as I showed earlier, would look like something like that, right? But we need another action called max pooling, which is you take the max. You take the max of the activation of these 2 pixels. Then you also take a max operation these 2 pixels. Right. And that means as long as the object is in these 3 pixels, then the value of this pixel doesn't change. And as long as the object is in these 6 pixels here, then the value of this pixel doesn't change. Does it make sense, or that's been unclear? So let's suppose that the value, so right now, let's say my input is 0, 1, 0, 0, 0, 0, 0, okay? I have some weights here, W1, W2, W3, right? Then after my multiplication, and then taking the marks, I end up with W2, okay? So let's say that this pixel gets shifted so that I end up with the input that looks like this. Right? Then after I multiply, this is W4, W5, W6. After I multiply, I ended up with value of W5, right? And my constraint over there is W2 is equal to W5. So that means the output of the network for these 2 images right here are the same, which is a desired property if you want to do object recognition when the object moves around in the image. Is there, yeah, you have a question?
So, in computer vision, when we apply a convolution filter,
Mm-hmm.
when we move the kernel to the next block, we move by 1 pixel.
Okay.
But here, we are moving by 1 complete block.
Okay. I draw this picture like this because it's clear to see. But you could imagine you move the copy just one pixel away, and that's fine too. Okay. For visualization, I say the step is basically equal to the size of the filter, but you could say that the step could be just 1 pixel away, and that is all fine. Right? All the mathematics I wrote to you here still applies. Yes?
Does this give you a way of handling inputs of variable size?
We don't have that yet. So if you have an image of variable size, you have to crop the middle part of the image and use it as the input here.
Or if you use convolution network, you can have a larger depth and you end up with
That's you can do it. You can do it. I'm saying in theory you can, but it's not it's not very common in the field. You could actually think about it that way. The problem is that if you have different size images, then the output image, right? Think about this one is the output image right here, could have also different size. And then if you move forward several layers, you want to do classification. And then the classification we're going to have variable size parameters, right? If you think about, you want to connect this to do classification. Right now you have 3 weights. But if it's variable size, you want to end up with 4 weights too. And that's what we can't do in machine learning yet.
So what you're saying means that every layer, the weights are different. They're not shared across the...
No, they're not shared across the layers. Okay. Okay. I have questions coming from you too. So yeah, go for it.
So, if we do forward prop as usual and back prop as usual, are we really saving any computation power?
Oh, I see. That's a good point. It turns out that CompNet is usually faster than dense network. So far, here I'm just talking about how to do mathematics, right? How to do it in an easier way to understand. But obviously, this operation right here can be called by some standard library called, you in MATLAB can call conf, right? And that's faster than doing explicit multiplication. That's the first thing, right? Maybe in conf you could do an FFT transform or something like that, so it's also faster, right? All sort of things that you could do to make it faster. But you should implement this thing first, and then you look deeply inside the code where you can optimize, right? And then start optimization, right? Because, yeah, I want to present the easier way to understand. Yeah. Any other questions? Okay. I need to clean the board. This one?
Yeah, if you look at one.
Like that. Oh, here? Okay, so a normal CompNet would be multiple layers, so it's not just that. So usually people construct a CompNet look like this. Right? You do convolution. Right? That's the convolution, and then max. Right? Max. And this can be considered as another output image, and then you can replicate this structure forward. Okay. What people also typically do is the idea of local contrast normalization. So what they do is that in addition to this layer, you take pixels here in a small area of the image, and then you compute the mean, and then you take the value and then subtract the mean. So basically, this value replicated here, but subtract the mean. The value replicated here, but subtract the mean too, and etc. And then divided by the variance or standard deviation plus some observer. So this idea here, subtracting the mean and divide by the standard deviation, is called local contrast normalization. So it actually mimics one of the very interesting property in the brain, namely that if you take an image right here, right, and then you also turn off the light, then that's with our recognition for that image is almost the same. So the light representing the mean of the image, right? And you could apply backpropagation using through the local contrast normalization, through the max, and so on as normal. But a deep convolutional net usually replicate this into many stages. Right.
Some people implement contrast normalization across filters, across layers of filters. And some people, so that would be, say, Alex Kozeski. Then Jan and Correa and so on in the paper, they implemented doing contrast normalization over the image.
Yeah. I think Jan LeCun, the guy who proposed the idea of neural networks and convolutional neural network, normally does this local context. So this is more standard. Doing mean subtraction and divided by standard deviation over locality is more usual. But it was Alex Grzybski who's the guy who applied this principle across filters. But I haven't talked about across filters yet, so I will visit that idea in a little bit. Okay. Is this idea clear? I want to make sure that you can at least do a forward prop, and once you can do a forward prop, you can work it out how to do a back prop.
Is the reason doing the subtraction and division by the standard deviation to have to work with smaller numbers? What I'm trying to explain, so that we reduce everything to a grayscale, so it's easy for us to compute. Why do we do that? Was my question. Why are we trying to? Why did we do the local contrast normalization? What did it give us?
So sometimes you take a picture of a car
Right.
when the light is on, and you take another picture of the same car when the light is off, a little bit darker, right? For you, that's the same car. For computers, that's a different car because that's such a nonlinear transform, right? Local contrast normalization will get rid of that phenomenon. Okay, I hope that makes sense. I think you take a picture and then you take another picture with dark and then you load it in MATLAB, subtract them, then you will see what I'm talking about, right? I have a question at the back. You have a sure. Go. So the mean across the pixels, yeah.
So it's the two, like.
Yeah, the mean of these two. So you take this value, you sum it up, divide it by 2, and then subtract that from this one, and subtract that from that one. Is that clear? It's the mean in in a local region of the image. Yeah, and the variance in the same local region of the image.
In practice, it's a lot more than 2, I guess.
Yeah. You could do it more than 2, right? You could do it like 10 by 10. Everything so far is just an idea, right? The size of the filter, you could make it like 10 by 10 rather than just 3 pixels, right? Yeah. Idea at the back.
All right. So we basically hard code lots of domain knowledge there.
That's true.
So this could not possibly, like, as it is, as you described it, it's not possibly it will work for like outside of the image recognition domain, right? Because we encode independent structure there and the contrast
Yeah.
and stuff like that.
Yeah.
So for like some other domain, we will
Yeah.
have to like construct the network. Like,
Yeah.
that.
Yeah. I think it's fair to say that a lot of these ideas in here are only applicable for maybe images, maybe videos, right? And maybe audio, right? Maybe some text, right? You could argue that it could be applicable for text too. But for general vectors, right? If this is just a random vector, then I would say that's not applicable. I think. Yeah. Okay.
No, I disagree with that. Because the principles that we're looking at here, which are translation invariance, local transformation invariance, intensity invariance, we often have to do that for all data sets. You need to get invariances. I mean, that's the basis of machine learning.
But if you do max Boolean, you do local receptive field for just a general vector, I'm not sure if that's.
I think it's important to do it if you're doing language or if you're doing any data mining classification task.
Yeah. Okay.
You always have to.
Yeah, I am more reserved, so I say it's all. I think I don't have experience applying this for all the domains. To be honest, my intuition is that it only works for natural data like images, video, audio, and text. But Nando said that it might be applicable for other vectors too, and I think that might work. And I don't know, to be honest, because I haven't tried it. So yeah, that I have limited experience applying this to general machine learning tasks. Yes.
How do you choose the convolution period? Here you choose that series. What's the difference?
So again, anything to do with hyperparameters. One is that I did a PhD and then I know how to set hyperparameters for neural networks. Okay, so a better answer is that you should use what I said yesterday about grid search, random search, and even better, Bayesian optimization. That's the reason why. Nando's talk should be even more appreciated. It turns out that it's non-trivial, right? This question comes up again and again and again, and especially in a CompNet, you not only have a couple of hyperparameters, you have tons of them, right? So you need a smart way to pick hyperparameters. And I think the work being done at Nando's group and some other groups suggest that if you use Bayesian optimization, you can come up with an architecture that's even better than human crafted network. How about that? And I think that seems to be very promising.
Does it depend on the image dimension or object size?
The Bayesian optimization is very general, right? So you take an existing network, maybe someone constructed it, right? And then it would play around with it, try a bunch of hyperparameters, and then suggest what the next thing you should be trying. But it's true that it's dependent on the data set. Yeah.
But that's okay. We call that contextual Bayesian optimization multitask.
Yeah, that's true. I have a question here.
Can local context normalization be applied as a processing standard?
Yes, people have done that. Yeah, that's a smart idea. Yeah.
My question is, how do you apply the back propagation on the max pooling layer? So how do you get the max function?
Yeah, one naive is you keep the index of forward prop, right? So which of the two would the max? And then you back prop, you only change these parameters, right? Yeah, makes sense. Any other questions? More questions?
To make sure, if the object is rotated, that's totally a different object.
Right. So again, this is limited invariances knowledge that you could actually incorporate in the network. Things like rotation, like scale invariance, are not incorporated, right? Because it's hard to do so, I guess. But you could come up with other kind of networks to do it. Yeah. Any other questions? Yes. Max? How do I choose max? Oh, because of this idea right here, right? The max. So after you multiply, you end up with a lot of values. The max only saying what is the most prominent phenomenon in the image that you see, right? You can work it out. So let's say you take 0, 1, 0, 0, 0, and multiply all this, right? Then you get some values, right? And then you get I see. Then the W2, we'll learn that W2 has to be also a negative number. We can take this offline. But okay, if you're not happy with the max, people also look at the mean, right? Look at the average between these two pixels. That's one thing. People try a lot of other ideas too, but I think the most prominent, the most successful is the max.
So are you grayscaling the image before doing this, or can you just directly apply to
So far I haven't talked about images yet, but we could get to that. It's hard to draw it in a 2D image really, but let's try. Let's try. Okay, so how to apply CompNet to 2D data, right? So let's suppose you have an image. This is a grayscale image for now, right? So you could have a filter and look at this part of the image. Okay, this part of the image. And then you have also have a filter that look at that part of the image. Okay. The CompNet saying that all the weights here are the same with all the weights here. So you can copy at every position and then replicate it, right? And after you do that, you end up with an image. Maybe I... So after you do convolution, you end up with an image. Is that clear? And then you do max pooling, and then you end up with another image, and etc. So the question is, this is a grayscale image. What do you do if it's like a 3-channel image, right? Valid question. It turns out you can stack 3 images next to each other. R, G, and B, right? You have 3 images. And this pixel, this neuron, instead of looking at one image, it will look through 3 images. Okay? So it will, when it apply at a position, it will see the red picture, green picture, and the blue picture. Okay? Is that clear, or is there a question? So, but it ended up with one image only, okay? Now, so one image is actually very limited. Can we do more than one image, right? The output here. So it turns out, yes, you can do that. You could apply the same principle, but replicate it into many, many maps, right? So you have another filter that look at this position, right? And then it will generate you another image. Okay? It's exactly the same idea, but it's a different filter. Okay? So you could draw this picture onward like this, right? So you have a stack of image at input. And then you have a stack of image in the output. And let's suppose that you have 3 filters per position, then you end up with 3 images. 3 filters. So the word filters to mean the weights that are associated with this neuron here, right? So here I end up with having 3 convolutional kernels or 3 filters, and I ended up with 3 images, right? And then you can do max pooling per image to end up with 3 other images, right? this is max pooling. And then you do local contrast normalization. Local contrast normalization. Now you have a choice. You could do local contrast normalization per image, or you could do local contrast normalization across images. Okay? And then you take that and then replicate it many times. So that's basically a ConvNet, right? I hope that you don't find that too complicated. Questions? No questions. Too easy or too hard? Too easy? Pardon? You have a question? Yes.
This is more to do with how you code this.
How code is?
So Mark and Liam have recommended this modular architecture where you think of objects, layers,
Yeah.
and each layer has a forward message, a backward message, and a derivative. So
Yeah.
these are your methods. And that seems to make sense. One thing that they don't often talk about is how to schedule visiting layers and so on for different optimization algorithms. And also, do you store the weights in the layer, or do you store the weights separately? What would you advise people to do when designing an architecture?
Okay, so first for a ConvNet, I implemented many versions, but I think your way of implementing, I think it's more modular and probably easier if you try different kind of architectures. But for speed, I usually implement this step. I usually call comp2, where comp2 is something like in OpenCV you have comp2, convolutional in 2 dimensions. I call comp2. In MATLAB, there's a function also called comp2, and then you call it, and then you end up with this, and then you do max pooling and so on. It turns out the backprop is also a comp2 as well. The backprop is also is a comp2, so I also call comp2 again. So the entire thing in here is done using comp2 if I code a convolutional net. Now for a general neural network, I think your way of doing it will be more modular. But this is probably one of the fastest way. Now behind comp2, what happens is that the library will check, how many images there are, what is the size of the filter, what's the size of the image. If the size of the filter is small enough and the image is large enough, what they do is they convert everything into FFT and then do it in an FFT. But if the filter is large enough, they will do it explicitly. So they take the filter and then do a for loop to multiply at every position in the image. So that's implemented when I do a ConvNet. But a general implementation, then you might want something else. Now I want to continue the ConvNet for a little bit. So it turns out that in a standard ConvNet will have many layers. So people usually do something like this, right? You take image, and then they say convolution. You draw something like that, and then you end up with the output, and then you do max to have max pooling, and then you do LCN to have something like that, and then many layers. You end up with maybe this is output of the last LCN, and then you plug it into a classifier right? So it turns out that a better classifier is like a two-layer neural network. So this is densely connected using rectified linear units, right? And then that's okay. And then after comp2, usually people also put rectified linear, and that's usually an architecture that people use to do computer vision these days. Is there any conceptual questions? Yes.
Go back to the case we were talking about using multiple images.
Yeah.
So what is a scenario that you want to go
So the
from multiple images?
So the input is multiple images because usually an image can be represented by 3 channels, right? Red, green, and blue. So you would rather represent it as multiple images rather than one, because one can only give you a grayscale image.
So the cases that you want to use multiple RGB images.
Sure. If you have a video, then you might have, per time step you have 3 images, and let's say you take 10 frames, then you have 30 input images, right? And then your filter is, instead of looking at one image, it should look at 30 images, right? Is that clear? Did I answer your question? Yeah, cool. I need question because I feel like conceptually it might be too difficult. Yes.
So how are the filters presented in the comment? You say that if there are 3 filters, how does it go into the learning process? So which part of the neuron? Does it have to do with the number of neurons that you tie together, or?
So let's say you have one neuron here in the network. It will look at the moment, I would say, look at this position, right? And they look at 2 images. So let's say this image would look like a 2 by 2 pixel, okay? This thing, I draw it out and I put it here, 2 by 2 pixel. And then another image would be 2 by 2 pixel. This is the first image, right? And this is the second image, okay? Is that clear? Now you have one neuron, which is this one out here, right? Right? It's gonna have the weights like that, right? It's gonna have 8 weights, right? It's gonna have 8 weights. And let's say we index it with W1, W2, W3 till W8. That 8 weights is going to be copied across the images. Right? Is that not clear? Cool. So let's talk about recurrent neural networks. Yeah. Tile? Oh yeah, sure. So right now what I'm saying is that the filters are being shared across the images. Okay? So they are exactly the same at every position in the image. So this 8 weights been copied to every position in the image. But sometimes you don't want that. Right? Sometimes you say, well, maybe only copy if it's very far away, something like that, right? So this filter will be copied if it's 10 pixels away. Then you insert that constraint in your optimization tool, right? So and then the nearby filters are just locally connected. They're not truly convolutional, right? So that's Thai convolutional net. Okay.
And how does it account for rotational effect?
So supposedly things like a Thai account, this is basically very good for translational invariance because the filters are exactly the same. So if the object moves left and right for a couple of pixels, because of the mark, because of the type weights, and then the max operation, it will be almost translational invariant. But if the weights are not the same, then you could learn rotational invariance as well. Because the weights are not exactly the same. You can pull over different weights.
Okay, but this has to come from the data.
Yeah, it has to learn from the data. Yeah. I have to move quickly to recurrent neural network. So sometimes that you have temporal data, right? And then you want to learn to predict using temporal data. So maybe you want to predict the stock market price tomorrow or something like that, right? So let's suppose that you have xt, which is the input at time t, and xt plus 1, that is input at time t plus 1, etc., and xt plus n at time n, right? So you want to construct a neural network that takes in information of temporal information. So one way to do it is using the convolutional neural network, and it looks like it's a recurrent neural network. It's something like that, and then you have so you have a set of weights W or the vertical direction, right? And then you have the horizontal connection as well. So you have two sets of weights, the vertical connection and then the horizontal connection. And the horizontal connection are the same, and then vertical connections are the same. And then maybe you want to predict the stock market price at time t plus 1. Okay? So this is called the recurrent neural network. Right? And then maybe, so in order to do back propagation, what you can do you do forward prop as usual, and then back prop also as usual, and then sum up gradient for W and V, W and U, and then update W and V and U using the sum gradient. Okay. So if you have a recurrent neural network, what you can do is you assume that all the U's are not the same. So you could say U1, U2, UT, and UN. And then you have W1, W2, WN, right? And then all you need to do, you do forward prop. You look at the difference between your prediction and then YT plus N. And then you do back prop. And then you sum up the gradient for all the UN, all the UIs, and all the WI. And then you use it as the update. Okay? I tend to draw that using another kind of figure. Another kind of figure that I tend to draw is something like this. This is the input, x times t, xt plus 1, xt plus n. Then I learned some represent. Okay, so this is another way to draw this figure over here. So you take your xt multiplied by w to get some output, and then let's say, so the representation at time t plus let's say t plus 1, for example, is equal to sigmoid of u times h of t plus w times xt. Okay. So this is h of t plus 1. H of t plus 1 is being the sigmoid function of u times h of t plus w times xt. So ht is usually recursively defined, right? And then you could do backpropagation. Yes?
So if I want to predict the stock market for the past 2 years, for every day or every time step, we end up getting
You could say these are stock prices of all the days in the past, and then this is the last day, the day of, and then you're trying to predict that. Now, this is basically, it can deal with variable length because you only have one set of parameter, u and w. So n could be any length, right? So if you want to predict the next month, you could use the same network, but you could, if you want to predict 5 months later, you could use exactly the same network, right? That I wanna come back to that in the following, right? So this is actually successfully used to do something called language modeling. So language modeling is the following. So language modeling is, let's suppose you have you read text, and then you have something called like the cat sat on the mat. Right? I went to school, etc. So the goal of language modeling is given the word, this word, predict the next word, and then given these 2 words, predict the 3rd word, and then given the 3 word, predict the 4th word, and etc. Right? And then start with a new sentence. Given this word, predict that word. Given these 2 words, predict this word, and etc. So given words from 1 to T, predict WT is 1. Really, right? This is the prediction task. It's called language modeling. Right. So for language modeling, so far we talk about XT being like real value vectors, right? But these are objects. These are discrete variables. They are just symbols, right? So how do we convert these words into XT, right? Some real value vector. So the way that people do it is using 1 of K encoding. So 1 of K encoding works the following. You take your dictionary, English dictionary maybe, and then, sort all the words, add VAC, and then ZZ, right? So this is maybe this is a 20,000 dimensional vector or something like that, right? This is 20,000. So let's suppose in your dictionary you end up with 20,000 words, right? Now, in order to convert one of the words to this to a vector, you can do the following trick. You take the vector and you look at where it is in this vector, right? Maybe it's at position 15,000. Okay? Maybe the word the occur at position 15,000 in your dictionary. Then the will be mapped into a vector where it's all zeros except for the position of 15,000. It's been at the position of 15,000, it has a vector of 1, and the rest is being 0. So this is called the 1 of K encoding. Okay? And that way, you can map every word in here to be a vector. Right? And also the output is also a vector. Right? And then what you all need to do is just put it inside this framework and run back propagation to do the prediction of the next word. Right? And it turns out that using this trick, we can achieve state-of-the-art prediction for the next word. Right? And this is useful for a lot of tasks. For example, machine translation. You need you also use it for speech recognition because it understands the context, right? And you've heard a lot of things about Chomsky grammar and so on, but it turns out that in real data, a lot of different kind of grammar doesn't work well, and neural networks usually works better. And it's very simple. It's just this trick right here. And the guy who is pioneer for this his name is called Thomas Mikolov. It turns out that this idea has been, a long time, and in 1986. That's a long time ago. So he's done it in around 2012 or something like that. I don't know. But back in 1982, in the first paper where people proposed the idea of backpropagation, they already talked about this idea. of one of K encoding and language modeling using recurrent neural network. Okay? Is recurrent neural network clear? One more thing. So after you multiply this vector, you take xt, which is a one of K encoding, right? For language modeling, you have one of K encoding. You multiply with W. That action is pretty much equivalent to selecting one column in matrix W, right? And then you end up with some representation. This representation here is called word vector. Some other people call word embedding. Because you take a high dimensional vector, you map it into a low dimensional vector, and then that vector hopefully can capture some semantic meaning of the word. And it turns out it does. And if you look at the word vector, and then you look at their nearest neighbor, right? You look at the word vectors, and then you look at the nearest. Maybe you visualize the W matrix for different word vectors. Then you end up to seeing something like this. The is close to Barack Obama, close to Bill Clinton, and Sunday, close to Saturday, and then maybe Paris, close to London. Something like that, right? You visualize W for each different vector, and then you project it in 2D or something like that. You would tend to see this picture. So it turns out that by doing recurrent training, and you also look at and do one of K encoding over there, then you end up having very nice representation for the words. Does it make sense? Yes?
For example, the strings were ordered alphabetically, but that doesn't matter. You gave us the example for the K encoding, is the word where?
Where is it? Maybe here. Yeah, okay.
Strings are ordered, but the order shouldn't be.
The order doesn't matter, because the order doesn't matter really. It could be any order. It's in an order so that it's easy to present, right? But every word, the idea is every word should be mapped into a one hot vector, right? All the dimension is 0 except for one dimension. It's not 0, right? Okay.
Can I ask you
Yes.
question about methodology? Typing question again.
Yeah.
At time t and t plus 1 and so on, you
Yeah.
also happen to, if you have a data set, you also happen to have y. So you have
Yeah.
y and t and y and t plus 1.
Yeah.
So you could
Yeah.
include those when
Yeah.
you're doing the training.
Exactly, right? So that's a very great question. So turns out that if you what people implement this in practice is called unfolding, right? So what they do is you have xt plus 1, and xn, and maybe in language modeling you're trying to predict xt plus n plus 1, right? So at here you also want to predict xt plus 2, maybe, right? And turns out that a good implementation is doing a feed forward and then move forward like this, and then compute backdrop at the same time, so that you save computation. And that's a better, it's much faster doing that way. Yeah, so you take every sentence like this, you do feed forward, compare with the answer, and then do backdrop. Yeah, so that's the actual implementation. Yes?
How do training data sets relative
the number of words in a dictionary.
Oh, usually the size of the corpus, it should be like 100 million words or something like that.
It would be usually something like exponential in your dictionary.
I wouldn't say that. Your dictionary should be like 100,000 or 20,000, but because it's unlabeled data, right? You can download any text on the web, right? This news, right? So that data set over here, right? You could get from news, right? Or any other website, and that you can get as many as you could. Usually we train with like 100 million words. The more the better. We also train with like 1 billion words, and the result is better. Okay. Yes. Set? That's a very good question. Yeah, right. So the goal is not trying to predict the backwards. So that's not called language modeling. You can do that, but it's not called language modeling. Language modeling is feed-forward that way. Okay? But it turns out that in order to just learn word vectors, you can do better, right? So here's an idea. So if you go onto the web, you search for something called Word2Vec. Right? Word2Vec is basically some program that read in a data set of text and then learn representation for every word. Right? If you download this program, then it's not a recurrent neural network per se. It's something different. So it turns out, before I move on and talk about that network, it turns out that recurrent network is very difficult to train, because if you have very long neural network, it takes a long time to do backpropagation, right? And then after going through many steps, the gradient vanishes. The gradient vanishing meaning that at the beginning the gradient is very big, but at here the gradient very small. So it forgets the information from the beginning. So it's very difficult to train. People notice this many years, right? So people have proposed many architectures to avoid the problem with recurrent neural nets, but it's probably not today's presentation. It's still a topic of research. So people want to get by the problem of doing recurrent connections. So another way to get by the connection is not to have recurrent connection, but have something like this. So let's suppose that you have xt plus 1, and xt plus 2. Learn some representation. Right, this is W, this is W, this is W. And then you do concatenation. This is concatenate or averaging to predict x t plus 3. Right, so instead of having connection that way, you do a feed forward that way. Right, so you don't have the recurrent connection anymore, but it's fixed size window on your text. And this idea is called feed forward. Neural language modeling. And then using this idea, instead of predicting xt plus 3, you could predict the word in the middle. Right? Or using the word in the middle to predict the word in nearby. So you could play around with all these tricks. So Word2Vec uses this idea. Okay. But the goal is not to do language modeling, but rather to learn the word vectors. Okay. Any questions? Okay. I want to talk a little bit about Google Brain, and hopefully I have time for that. Zico? Zico is not here. Alex, can you help me? Can you help me drop it out? It's exciting. Okay, so the last part of the talk we will have a lot of pictures, and it's gonna be more entertaining, less math. Okay. Okay, so I'm gonna talk about some ongoing projects at the Google Brain project. So first, I want to start by saying that Google uses a lot of machine learning, right? And it uses a lot more machine learning where more than what I can imagine when I was in grad school. So, you know, when I was in grad school, I thought, oh, Google uses a lot of machine learning. It turns out it uses even more than what I can imagine. But machine learning is very, very difficult. Right? Machine learning difficult is because you really, really need to require some domain knowledge, domain expertise of the problem. For example, if you do image recognition, you hire people who got their PhDs in computer vision to do design features, right? And then train their model on vision data. But then if tomorrow you want to do video recognition, then you hire a bunch of other people who got their PhDs in video. And then the day after tomorrow, if you want to do speech recognition, then you hire a bunch of other people who got PhD in them. Now, it might work for the current applications, but maybe in the future, for things that we haven't got PhDs for, it might not work. Moving backward in time, a few years ago, when I was a PhD student at Stanford, I thought it would be really great to actually learn representations. So instead of hard coding features, use deep learning, whatever we've seen so far, to learn the features, right? It sounds today that sounds like, you know, a trivial idea on the hindsight, but it never really caught on in, pattern recognition, in mainstream pattern recognition. So it's up to, 2011, people still do handcrafted features for a lot of domains. But for us, deep learning works right. It works well for many, many small problems. It works well when you increase the amount of data, all right? Because it has a lot of parameters. If we increase the size of the model, it works just better. And the good part is it requires less domain knowledge. So around 2007 and to 2010, I was at Stanford working on small-scale deep learning, and it works out pretty well. So Google came along and expressed interest in using deep learning in larger scale. And it turns out the result was very fascinating. So again, the idea of deep learning is to learn representation, layer representation all the way to the top, right? You take X, multiply by some matrix, apply some nonlinearity, get the output, and again, that is the input of the next layer. What beautiful about this approach is that if you talk about it in computer vision perspective, what it's trying to do is to try to learn representation. For example, at the first layer, you will see something like edge detectors, and then onwards, you want to see high-level concept like face and cat neurons at the top. So at Google, I work on something called disbelief to represent the fact that I didn't believe that it should work, right? So I came up with the name that we came up with a name that to reflect that we couldn't believe that this thing gonna work, so we just try it out. But it's distributed belief networks. So the idea is the goal is to train deep learning on many machines, like maybe 100 or 1,000 or even 10,000 or even more, 100,000 machines. And the model is what I've told you earlier. It's a neural network. And there are in neural networks, in general, there are 2 steps that you have to do. You do forward prop to compute your prediction, and then you do back prop to compute the gradient, right? That's all you need to do in a neural net. So to parallelize the training of the neural network, what we do is we use 2 ideas. The first is model partitioning. So you take a neural network, and then you divide it into many machines, right? And the first machine will be responsible for computing the values of these neurons. And then the second machine will be responsible for computing values for these neurons, and etc. Right? And then obviously there will be communication across machines, but we can design the neural network in such a way that communication will be much smaller than computation. Okay. And then per machine, we also have multiple cores to do computation. Okay, and this idea can use up to like 1,000 cores or so, right? But 1,000 cores is still slow, right? We want more. We want faster. When we train this model, I realized that it would take months to train a neural network on images, or months to train neural network on speech recognition. And again, this is important because if you train a neural network that takes several months, then if you want to change your mind, right? Maybe the experiment doesn't work out. Maybe the hyperparameters is not good. You want to change your mind at some point. Then if it takes several months, then you have to wait several months to do something again, right? That's undesirable. You want to scale down that training to be like a couple of days, right? And that's what we succeeded in doing. So the way that we do it is to add more parallelism. So imagine this is one model that we had before. We take our data set and split it into multiple chunks, right, partitions. So let's suppose that we have 3 million examples. So the first chunk gonna have the 1 million examples. Second chunk gonna have 2nd million examples. This is 3rd million of examples, right? And then we're gonna train independent models on each of these data set using stochastic gradient descent, right? And then instead of making the update, at every step we're gonna send the gradient to something called the parameter server. So I think Mu Lee has talked about the parameter server so far already, but the idea is simple. You have a few hundred machines sitting in the middle, waiting for the gradient to come in. Right? The gradient, namely P prime. You wait for P prime to come in, and then delta P to come in, and then make the update and send back. So the conventional way of doing this is the parameter server gonna sit in the middle, wait for all the answers to come in, take the average of the gradient, make the update, and send back. Okay, that's the conventional way of doing it. Now the flaw of the conventional way is that let's suppose that one of these machines or one of these copies will be slow, right? If one of the machine will be slow, and this is real, because let's say if you run your model on 300,000 machines, if the probability of your machine being slow once per year is, is 1 day per year, right? Then if you run it on 300,000, the chance of having one slow machine is actually very high per day, right? You multiply the probability 300,000 times. So it's undesirable for system that has a lot of slowness and delay and etc. So the way to counter that is to have asynchronous communication. So asynchronous communication, again, the conventional way is to wait for all the answers to come in and then take the average and send back. Now, we don't do that. What we do is at any moment, if any answer comes in, we make the update to the parameter right away. And then, after a few hundred updates, we broadcast the parameter back to everybody. And then everybody replace their own copy with a new copy. And then and then compute the gradient again. So it creates a lot of asynchrony inside the network, but it works out just fine. And this way we can actually improve the speed, almost linearly with the number of copies. Okay? Is this idea sort of clear? Somewhat? Okay. So at Google Brain, we try a lot of ideas, but it turns out that the simple ideas work out very well. Right? And the two main ideas that we have was model parallelism, which is take a model and then split it into multiple machines, and then data parallelism, and then communicate using the parameter servers. That's the two ideas. And right now, we can use up to 100,000 cores or even more. I think 500,000 cores is possible now. And because of the speed, so we can scale down the training of something that takes several months to a couple of days. And because of speed, we can make a lot of breakthrough in many applications. And I'm going to show you next the applications. Right? So the first application is a voice search. So it turns out that one important application for Google and many internet companies is to understand what you say, right? You look at the phone and you talk to the phone, you say, who is Barack Obama? And the machine has to transcribe that into some text and then do the search, right? To do that, it turns out that a conventional speech recognition pipeline has two components in it. Component number one is they take one window in the speech. Let's say the speech is some waveform, right? They take some fixed window like that and then do some classification to something called a phoneme. So it turns out that human speech has about 800 phonemes, maybe more, like around 800. A phoneme is a subword. It's not a full word. So for example, if I say Palo Alto, in fact, the phoneme corresponding to that is Palo Alto. Yeah. So there's a lot of that's a lot of effort to So linguistics actually figure out that there's 800 phonemes. I don't know why. Okay. So the task is to trying to have a model to convert the raw input into a phoneme. And then the second model is called a language model that put all these phonemes together to come up with Palo Alto. Okay? So maybe from the raw speech you say Pala Alto, right? But Palo Alto is more likely. So your prediction would be Palo Alto. And the language model is a recurrent neural net, by the way. Okay? It's going to be trained on text. So the acoustic model used to be a shallow neural network or a shallow architecture. It doesn't work very well. But recently we trained a deep neural network, fully connected, maybe 12 layers, and it works very well. It reduces the error rate significantly from something that doesn't work very well to something that you have today. So if you interact with Android voice search, that's basically the system you have here. And before this belief, it took around, I don't know, a year, half a year to train, but now should take like a week to train, which is quite good. And that's the reason why we can train with a lot more data too. And now you can use it in Android voice search. The second kind of application that we use is in language understanding. And there, we want to learn word vectors. And the word vectors is basically what I presented earlier. We want to learn representation for words so that it can keep the semantic of the word, right? So you want well close to dolphin, Obama close to Clinton, Paris far away, but maybe close to London, right? And the neural network that we have is very similar to what I presented just before this talk here. It's basically for every word you map through a matrix, and then you concatenate, or maybe you take the average. Maybe you give it through some hidden representation, and then you do classification to predict the last word in the sentence. Simple. And it works out very well. We trained it on 1 billion words. And if you type in, and we have an interface where we can look at nearest neighbor for all the word vectors, right? And for example, the nearest neighbor for the word apple with the small a is all kind of fruits here, right? Berries, blueberry, peach, melon, etc. But if you replace with the capital A, Apple, the company, then you end up with Apple's products. Okay? iPhone will be close to iPhone and other Apple products. Okay? So not only the distance between the vectors makes sense, the nearest neighbor makes sense, but the difference between the vectors also makes sense. For example, if you project the word vectors into 2D, and then look at the difference between Spain and Madrid. Madrid is the capital city of Spain. And the difference between Italy and Rome, and then you compare them, it turns out they look very similar. Right? And this is very good for relational extraction, in the sense that let's suppose that I don't know the capital city of Italy, but I know the capital city of Spain. Okay? Then I would take Spain and subtract Madrid and get a vector, and then add that vector into Italy, and then maybe end up here, and then maybe I do nearest neighbor, and then end up with at Rome. Okay, and you can use it to learn word vectors for people, right? You can learn word vectors for Barack Obama, you can learn word vectors for Britney Spears, and then you can ask about all information like profession, age, birth, etc. Right? Using this idea that I show here. Is this clear? Okay. Yes. Multiple meaning?
Yeah, because a bank
is
a very different
Yeah.
point in that space depending on its meaning.
Yeah. I don't like that question. But I'm forced to answer it anyway, so I will try. Okay, so the question is, what if a word has multiple meanings? Okay, the word bank has multiple meanings, right? For bank, Bank of the River, and Bank of America, right? That's the like money thing. Right? So if you learn one word vector, then money and river things put together inside a word vector. So it seems undesirable, I guess. First, in practice, it's not a huge deal because it's high-dimensional vector. But anyway, we want to fix that problem. So the way that we fix that problem is in the word vector model, this word vector model right here. During the feed forward, for every word vector, you say every word has 3 meanings. Every word has 3 meanings, and during feed forward, you will have a choice to pick the best meaning to give to the network. So out of 3, pick the best one. So all sort of combination of all the words, and pick the best one, and then when you do backprop, only update the word that give you the best prediction, and that turns out to work just fine. Does it make sense? I hope that makes sense. It seems kind of clever, but it's not that clever. But it works out very well. You have bank, one bank close to river and etc. One bank close to money company and etc. Okay, we never published this idea, by the way, but I think if you use it, it works out just fine. It doesn't seem satisfying. It doesn't seem satisfying for every word to have 3 meanings, but in general, if you make it 5 meanings and so on, it solves the problem. But the combination is too high, right? Anyway, the other application that you could use is machine translation, right? It turns out that if you learn word vectors for English, and then you learn word vectors for Spanish, and then you visualize them, and what you see is that they look very similar, the word vectors in one language to the other. For example, here, let's suppose that I know the translation between of 1 to 4 from English to Spanish, right? Then I could learn the linear mapping between this here to this space, right? The linear mapping can be done by just linear regression, one command in MATLAB, right? And then let's suppose that I don't know how to translate the word 5 to Spanish, then I could take the linear matrix that I just learned, apply to that vector, and then end up somewhere here. And then if I do nearest neighbor, then I get the word 5, which is the translation of the word 5, right? So you can use word vectors to do translation as well. Okay?
In your practice, when you were trying these things out, what are the other words that come in the neighborhood of that point? Say, let's say about 5, when you try to project the translation of 5 onto Spanish.
Yeah.
And whatever that point was,
Huh?
5 the closest, were there other closest points? I'm trying to understand what is the precision of this. Like,
Oh, the precision is about 90%.
90%.
Yeah. Yeah. So we run a lot of experiments. There's a paper on this topic. We run a lot of experiments, and we using a dictionary of 6,000 for start to learn the linear mapping. Then trying to translate the rest of the dictionary, we can get 90% correct. Okay? Sounds good. So we have a paper. You can find that online. Okay. So the third application is in object recognition. So turns out that if you upload an image to Google Plus or Picasa, or maybe if you upload a video to YouTube, then there's a network that look at the video and analyze what the content in the video, right? And it turns out it's basically a local receptive field neural network and a convolutional neural network we're talking about. There are 2 papers here, and they run. There are 2 neural networks that look at the image, come up with a prediction, and then average the prediction. There's a paper in 2011, and New York Times talk about this result, the fact that we can detect cat on the internet. The cat result was a simple autoencoder on the images of YouTube, right? And then we do object recognition. Maybe I can feed forward a little bit. I think the result is very significant. Like on an ImageNet dataset, the best accuracy that people have, 20,000 categories, right? 20,000 categories. So for any object in every word in dictionary, you have, a set of images. The chance, if you just give an image and you keep saying cat all the time, You get 0.5%. That's very low. So if you get 10% by working very hard using handcrafted features, right? And then if you use neural networks, you get around 30%, which is much better than handcrafted features, right? And by the way, 30% is 30% on 20,000 categories. So you make a prediction, right? And if it's your prediction of 20,000 categories and it's wrong, even if you predict cat, and if it's like some other type of cat, then you're just wrong, right? And for that, we get 30% accuracy. And the network does amazing things. For example, this image right here, when I sent to the network, it says seat belt. And in order to understand that this is a seat belt, it not only understand, this is the seat belt, but only understand that there's a guy who drives a car as well. For this image, I say that's a chair, but the network say it's a Boston rocker. So it's a specific type of chair. So this it's a accurate. I think that's good. This image right here, I couldn't even tell what that is. But the network somehow figured out that that's a shredder. It's a paper shredder. That's kind of hard because you need to understand that there's some paper right there. And imagine you write a program, right? To actually write a program to recognize this is a shredder is kind of complicated, right? But learning does better than that. So I think that's a remarkable result. So we thought that it's kind of lucky because somehow it does so well. Can we fool it by sending it like cartoon pictures, right? Because during training, we restrict the network not to see cartoon pictures. So at test time, we give cartoon pictures and see what it does. And it works out very well. So for example, this image, it would say that's a face. That image, that's a amusement park. That image, it say that's a hammock. I think that's a hammock. One could say that's a cat too. So for the things that it doesn't do very well are objects that are very similar to each other, right? For example, it will be confused between Indian elephant and African elephant. I have no idea. I actually ended up reading Wikipedia to distinguish between the two. And then it couldn't say, cassette and tape, malaria mosquito and yellow fever mosquito. I really don't know. It also does badly for objects that are very small in the image, right? For example, this image right here in ImageNet is labeled as a plunger, that object right there. The network say that's people, okay, reasonable. Things like this image right here is labeled as snorkel. The network say it's a swimming, maybe it's a person, and then swim trunk, and then snorkel. Too late. It's a snorkel here. So this image right here, the network says people, then tree. We look at the top prediction, right? The first is people, the second is tree, third is street, and then matching order, and all the way to the end is a basket. Too late. It's not good. So this image right here is labeled as ping pong ball. That's a ping pong ball. Okay. So there's a lot of idiosyncrasies in the data set, but in general, the prediction of the network looks fine. Okay. When we use it for Google Plus photo search, right? A friend of mine has a lot of dogs, and she uploaded a lot of dogs photo in Google Plus, and then she searched for dog without labeling the pictures of the dog. And the amazing thing is the networks return her pictures of the dogs, right? That's a small picture of the dog, right? Then that's a close-up picture of the dog. That's the dog close-up. It's all kind of picture of dogs. That's amazing. And she's so excited, and she sent me this picture. So I sent that. I give it to you so that. as a proof that it works. Okay, so I ran out of time, but I would say at Google we work on scaling the training of deep neural networks. We use two ideas: model partitioning and data partitioning, right? And this is the picture that you might remember. And then we applied it to voice search, photo search, and then text understanding. And we made a lot of significant improvements on these applications. And Google Brain is a big team. We have about 20 people, 20 or 25 people working on different ideas of neural nets and so on. Okay, so I can stop here and might be taking questions from you. Any questions? I'm so happy that it's clear. It's not clear.
Why did Google spend so many resources in 100,000 cores and we as CPUs might not go for the GPU?
Good question. It turns out that parallelism across machines and GPUs are like orthogonal ideas, right? You could apply the idea that I told you instead of on machines with CPUs, machine with GPU too. Same thing. We are actually doing it, so yeah. Question?
So that's 30% accuracy is basically for all the categories of
This is for all categories.
Okay.
For in ImageNet, the size of each category is got a balance. So the number of people in the data set is the number of people images in the data set is also equal to the number of baobab tree in Africa, right? So it's the same. Yeah. No more questions. Okay, great.